And thanks to GMG for asking us to present. And what we're doing is presenting one of the research projects, or one of the flagship research projects from Molycop Innovation. And in Molycop Innovation, our portfolio challenge is to leverage our existing capability to solve the social and fiscal challenges of our customers, the miners. And this will result, of course, in new products and services and different portfolios. And we've seen really good presentations tonight, which I really enjoyed from Neville and Rodrigo. So one of the portfolios that we're examining to try and help our customers in their social and fiscal challenges is harnessing the digital transformation that's happening in mining. This presentation was from in GMG in 2019, so one year ago. And we chose it because it gives a good context to the research project. And I would just step through now what the project is about. Okay, there we go. So firstly, the technical importance of the project. For those that don't know, mineral processing consumes about 3 to 4% of the global energy produced in the world. And of that 3 to 4% of the world's global energy, around 36% of it is in comminution processes. And the comminution process within mines consumes over 2.5 to 3 times the energy of any other process within the mine. So we focused on that, and we have an ambition to significantly and seriously reduce the energy consumed in the comminution process, which gives rise to our project. And this presentation that we've chosen was received a high commendation from SAG in 2019 because of our aims. And of course, energy efficiency is not new, and it's been the topic of many researchers from, the early 50s with Bond, through Morel, and through some of the presentations that we saw through Neville, and of course, Rodrigo earlier on. Interestingly, most of these studies rely on empirical findings with a base in laboratory, or they suffer from this inability to actually measure the dynamics of what's going on inside the mill. So these are all inferred results inside the SAG mill. Slowly, it's slow to move. Okay. So people have tried to measure inside the SAG mill before. So work was done at the University of Utah, Rajamani, and one of the departments of energy in the United States. And then another attempt was made to measure inside a mill by Peter Radochesky and Suda Martins, McGill University, and they actually built a ball sensor and out of aluminium and plastic, and they tried to make that sensor system work, and they proposed that this sensor that could be put inside a ball would measure for a very short time, but wouldn't really represent the dynamics of an industrial SAG mill. So what we did in this project was we've successfully secured in-ball measurement from within an operating SAG mill. And we've been running a project now at an operating mill in Western Australia, where I am. I'm at the mill today. That's where I'm having the call from. And we are analysing data from inside the ball inside the mill as it moves around to try and understand and improve mill optimization modeling, and separately to try and improve on-site decision making. So just move to our next slide. So where the best practice for understanding and measuring inside the mill has certainly been assisted by technology and the development of discrete element method modeling. And these are simulations based on mathematical modeling and energy movements within the mill, but they tend to be highly constrained in that they're situational, they assume steady state, they suffer from difficulty in validation, the actual DEM process, and we use DEM within Molycop, and we use it to get insight into the right questions to ask, and we combine that with our own mill optimization toolkit, etc. So we're not opposed to DEM at all, but we understand that gives us really great insight into understanding the constraints of DEM and what it's used for and how it's used, and the standard practice in real life for mill modeling and comminution is a paradigm really of throughput and trying to connect power draw and throughput as a coverall approach in a really, really complex system. Whereas if you could measure from directly inside the mill and connect that with the mill measurements that we've seen the likes of Rodrigo present today, and some of the research work that Neville presented, that Marsden's doing, that Motion's doing, we think that this could be a real game changer for the industry, and achieve our ambition of seriously reducing the energy consumed in the SAG mill. And I get it. I do understand the non-SAG community, and we're really aware of it. The sorts of things that Neville talked about in the high voltage pulses and various other technologies to change mineral processing, and we think that has merit as well. But we've got these particular plant and equipments in play; they exist, and if we can measure inside the mill and work together, I think that we could seriously change the energy consumed by this plant equipment. These are our ambitions. And so that's, that brings us to this slide, really, the importance of the project. So we heard about these social and fiscal challenges, really, really well articulated by Neville Plint, significantly better articulated than I'm going to do. And then we've got a host of technology, automation, data analytics, big data, the virtual mine, remote operating centers. And so we're about harnessing that digital transformation, bringing together this technology with this ambition focused on a particular project, the SAG mill, to measure from inside the mill and deliver real results. A sensor system that improves theoretical modeling and provides results that can be seen in real time can facilitate skills and decision-making of plant teams, industry associations, research bodies, and this possibly means significantly more for less effort. Okay, so this is what our methodology is. This is what we have been working on. So you can see what we do here is we actually insert sensors inside the SAG balls, and Molycop, of course, being the largest manufacturer of forged grinding media in the world has the SAG balls and the carriers. We've developed the technology. We don't need to insert sensors inside every ball. As a matter of fact, in the mill that we're currently working on, which has over 2,000 balls, we're getting, pretty good results from 8 to 12 balls. So it's not every ball that needs a sensor, it's just enough. And then the sensor from within the ball sends a signal. The signal can work with the tags that we fasten to the liner bolts, or it can work independently. It's captured by antennas. One of those antennas is positioned within the feed chute of the SAG mill. And then that signal, it's a digital signal, and it's sent to a data receiver where there's some edge server processing. It's cleaned, it's sent to the cloud we're using an OSI Pi historian, and then it's made into variables and projected onto a slave screen for the operators at plants to see. And then we also use that data and do a couple of data analytics projects. This gives you insight into, so here are the balls and here are the tags inside the balls. So this is a sensor. It's about 76 millimeters long, and then this is in rods. So we ran a project in a rod mill for 12 months as well. And then these are the bolt sensors, so they fix onto the existing bolts. You don't need a different bolt, so that's great for all SAG mills anywhere. So we literally fasten them on, screw them on. We have a bracket to attach them. And so these give you the feed, middle, and discharge, and we see those results. So we can see the balls inside the mill and the impact quanta and the impact count of balls within the mill. And we can also see from outside the mill the motion, the charge motion between the feed, the middle, and the discharge end of those balls when they're moving, and that infers the movement of the charge. These are some of the very early results that we've got. So these are results from a 125 millimeter ball within a mill and a 94 millimeter ball within a mill, and we have a reference tag, and then we got temperature, and then we have the number of strikes and the size and the scale of those strikes, and we've broken that into three sort of strike quantas. And what we can see is, as the energy inside the mill picks up, we see a change in the incline of this count impact graph, and so that's a great telltale sign of the increased energy within the mill. And we've done a lot of work around temperature, and what we found was the temperature really closely maps the slurry temperature, and the slurry temperature really closely maps the outside temperature or the ambient temperature. So we were hoping to get, a measure of energy or energy transfer, or, see something from that temperature measurement inside the ball that connects with energy dissipation. But what we got was a very unique temperature measurement or thermometer inside the mill, which you can get from the slurry temperature anyway. So we have moved on from using temperature and focused on these other variables now. And these just showing you some of the early results and some of the work we've done working on the inferences and the trying to connect the operation of the mill, what the mill is, what we're seeing in the mill, what we call a mill event in our language. So a change in the performance of the mill, or a change in the performance of the operating state of the mill, and then connecting that to the data that we're seeing from within the mill. And this is rod mill data, and we were measuring impact and tilt in this case. So for a rod, tilt was the different, the difference between the 180 degrees, and we were finding rods were moving more than 1 meter from horizontal, which takes a lot of energy, so that was interesting and early days. What overall our ambition is to understand all of those mill events, all of that variability in the mill, and then connect that to root causes, and then to try and remove two things: either try and remove the variability or what's causing that through operator behavior, so things the operator can do, or if we can't remove it completely, then let's reduce the variability cycle time. So what we mean there is, if let's say you're processing and you hit a period, never talked about this, of different competence ore, or a different ore that you were not expecting, you'll see the characteristics of your mill change. And that cycle time of change might be hours. It does not change for a short time, it changes for hours. So if we can measure that, and if we can measure the energy inside the mill with what we're doing, connect that to these mill events, and give the operator something that he can change, then we can reduce that variability cycle time or reduce the mill event completely. So that's we're working on that. Of course, what are the consequences of that? So the consequences of that is, if you can reduce the variability of the mill by looking at the measuring inside the mill, then you reduce these extraordinary wear events, where most of us are very familiar with these sorts of displays, where you've got a great cascading behavior here, hitting your impact toe, then your working toe, and you've got these particular zones operating within the mill, which Little proposed early, and then Odell, and where is the best and most energy efficient comminution around these zones. And what we don't want is these cataracting behavior, throwing it onto the lifter bars, onto the liners, missing the working toe, and delivering you these extraordinary wear events. And measuring inside the mill gives you great insight. We found great insight from measuring from the sensor systems measuring inside the mill in these cases. And then, of course, if you can do this, reduce that variability, reduce the cycle time of the variability over a longer period, and measure that, then you create this real value for stakeholders. You'll get an improved throughput, you get an increase in energy efficiency, you'll get improved operator decision making, and you'll reduce these extraordinary wear events. So you're getting top line revenue and bottom line reduction in costs, which is, which our ambitions are, really significant for the mining teams. So your fiscal responsibility and your social responsibility targets are being met by delivering these ambitions. So these were the conclusions at that time. The commercialization of the project, or the proof of concept, or the attempt to commercialize the project, has proven that a sensor system can deliver real-time measurement from inside an operating mill. We have 2 mills in Australia operating with SAG balls and tag bolts measuring inside the mill. We'll deploy one in South America at the end of the year. That'll be our 3rd mill. The system is incredibly robust. It's reliable. The sensors read the data. The sensors last for a period of time long enough to give us meaningful, robust and reliable data. Our initial results show us that we can connect mill events and with the SCADA data. So we also draw in the SCADA data line and throw that onto the dashboard, and we can connect very well what we're seeing from the measurements inside the mill with mill events and changes in operator practices, like we talked about the ore blends, oxide runs, changing the crusher, setting the crusher gaps, these sorts of things we can actually connect to energy changes within the mill as a result of what we're seeing. And then if we can triangulate these results, so if we can get the real measures, use the existing modeling tools and the digital platform that's available and triangulate these results, then our ambition is that's going to make a big difference and create real value for the miners, for the stakeholders. We think the system's got the potential to contribute to the industry as well by facilitating on-the-job learning, of what's going on inside the mill. So we've got this really strong change in skills, transition of skill sets, and people depletion at mines these days. And if we can give them a tool which lets them look inside the mill, look at the energy inside the mill, and make the consequences of the things that they're seeing front of mind for operators, then we're going to get an improved operator as a result, is our thinking. And then the trials and the quantification of a benefit model continue at the West Gold sites, exactly where I am today. I'll just move on to the next work. Okay, so the next step for us was to increase the technology of the system to include trajectory measurement. So we've gone, this was 1 year ago, so we continue to go down that path. We are working with the University of Sydney's SkyGem team. We did X-ray tracking to try and get a ground truth for where sensors might go in the mill. We used we built a mini lab, very small scale, and then we used X-ray tracking, and then we also used a RFID sensor, and we overlaid those on top of each other. And so we will release a paper on that work. We are quite optimistic about being able to have the trajectory of a ball measured from inside the mill in a graphic on a screen. We think that's really realistic, and that we think will significantly help the DEM modelers and the empirical modelers in their quest to validate their models. Algorithm development, supporting AI and machine learning. So we have two streams of data analytics. One stream is in operating states. And so what we've done is identify operating states of less variability and operating states of high variability. And then we've looked at the moderating variables that affect these, and we've been successfully able to build a model zero with machine learning algorithms that can show these two operating states and then pick a transition point, or what's called a change point, between these two mathematically modeled operating states. And when we do that, we can send an alert. We can say, the machine learning algorithm identifies that you're moving into an undesirable operating state, and you might want to do these things with these variables so that you avoid that or you reduce the variability cycle. The other stream that we've done is in decision rules, and we'll present a paper at PRUSIM in 2020, which has already been recorded around decision trees and importance. And so this allowed us then to take a whole lot of data and then do a heritage style circuit analysis. And then we kept those two things separately, and our data team came up with essentially the same behavioral rules that the heritage circuit analysis team came up with for an improved operation. and specifically this was about bypassing the pebble crusher and putting scats on the ground versus, not doing that behaviour. So that was a really interesting thing, and we'll present a paper on that. And then we're continuing to design experiments in real time using various DEM simulations and these sorts of tools. And we're just trying to connect those with, the actual measurements from inside the mill and the modelled measurements using these simulations. We've got a fair journey to go on that one, I must say. We have connected real-time measurement and mill events to confirm that there's benefit in this. We're trying to quantify exactly what those are. I saw Rodrigo do a great job assigning the improved throughput to the data analysis work he did. We want to do those sorts of things with the measurements from inside the mill, connect them up to quantifiable benefit. So obviously then we turn our research project into a saleable product. And then we do want to secure more collaboration partners. As I say, we've been working with SkyGem. We'll have a PhD student from those guys working on developing a new energy efficient measure using measurements from within the mill. And we've also got a PhD student from West Australian School of Mines, Curtin University in Western Australia, working on mill monitoring and data analytics using the data feeds from the balls inside the mill. So that's his topic of his PhD. And we're absolutely interested in more mining teams and associations to work with, to progress, to realise the step change that we think might be possible for the industry from measuring inside the mill. And so that is that's our concept. That's where we are. We've certainly done in the year a lot of work that gives us a lot of confidence in realising our ambitions. I think that's where we're up to, Dominica.
Perfect. Thank you so much, Paul, for the presentation. We actually have several questions for you. Just to be mindful of time, we're gonna answer a few, and then I'm gonna send you the rest through email so you can help me answer it, and then we will distribute them among the participants. So the first question is from The first question is from Munson. How would you validate the measurement of the instrumented balls in industrial scale?
Yep. So the way that we're validating is that we deliver what's called a base case. So we go and take a lot of the data and just develop a base case of how that SAG mill is operating right now. And we look at the variability. So the mill events that are causing variability during the base case. And then we deploy the balls within the mill. And over a period of first we establish that data can be captured and realised and thrown on the screen. And then we look at that data and identify and connect it to mill events, and then make attempts to reduce the variability, firstly of those mill events or the variability cycle. And then we run another circuit analysis using the tools and we look at the differences in throughput between one, the base case, and two, the case when you were using the data and making different decisions. And we see the changes in things like throughput, wear, and energy efficiency. And then we have to go through this really tough journey of assigning that to the actual data that was measured and the decisions that people were making. And that's where we're up to. because the miners themselves and the teams are constantly trying to improve their operations, and they make decisions about their ore blends, about their training of their operators, et cetera, et cetera. So that's where we're up to. We think we have one case study where we quantified that, and we think our improvement was at least 1 tonne per hour, at least from just good decision making. And of course, it was Rodrigo who told us tonight, which we believe, small changes, big gains. You make small changes to the mills, you get big gains. And so that's how we're doing it.
Perfect, thank you. There's another question that I kind of missed. Have you seen any difference in charge motion inside the mill along the length? What those observations tell?
Yes, we have. Yes, we have. So in different times of running different types of ore, we'll see different energy at the feed end and the discharge end. So we'll see a higher impact and numbers count at the feed end for a particular type of mill. For example, like an oxide ore, you'll see your disturbances are all feed end, because that oxide ore is breaking down very quickly and going through the mill, and we're not getting a lot of energy through the discharge end. We're just getting a normal amount. Whereas if you put a highly competent ore in, you're getting a lot of energy in the discharge end and less in the feed end. And so because we have those 3 measurement stations and we do the differential between them, we are getting insight at this stage. We need to do some more work, but we're definitely seeing these.
Perfect. Can you measure the ball motion in 3D space inside the mill? Can you tell the event if the ball hits the liner?
We are trying to measure in 3D space inside the mill. We're calling that trajectory. We're calling that a trajectory graphic. When the ball sensor data disappears, it's as meaningful as when it's there, because that's telling us that it's now disappeared within the charge. And we're very fascinated by what we call the little zone, or what's known in industry as those comminution zones within the SAG mill, and where the ball is traveling within those zones. For example, if it's in that dead zone, it's just going to rotate at the same speed as the rotating mill, which we can obviously measure. If it disappears for a period of time, our sensor will backdate, but the fact that it's disappeared and for how long it's disappeared gives us as much insight as measuring where it is. So yes, we can is the answer. How does that create value, knowing where it is? Need to do some more work.
Perfect, thank you. And one last question. The rest of the questions will be answered offline and shared with the participants.
Sure.
So the last question is, what is the life of the what is the life of the charge tag?
The life of the charge type.
Yeah.
Not understanding the question, Domenica. What is the life of the
I don't know
charge?
if Bandakini, I don't know if I said your name correctly. If you can maybe unmute yourself and ask the question.
Sure.
I think they meant the sensor, the instrumented ball. What's the life of that instrumented ball?
Okay, sure. So this depends on the dynamics of the mill, but the life say the rubber line mill, which has a variable speed, which has less variability in its blend, is over 30 days. Some of the sensors in the steel line mill with high variability in the ore blend are lasting 14 days to but it's quite variable. And so you don't Yeah, that's a good question, and I'll just give people some more insight. So you keep charging balls in, you know, at a rate of 4 or 5 balls a week, and we have to, you know, you have to work that rate out depending on the dynamics of the operating mill at the time.